Okay, welcome to the crash course. So I'm running this hybrid, so there's a computer I might be talking to sometimes, and I'll also be talking to the room, so just feel free. You guys can just ask if you have questions. People on Teams, just feel free to chuck a message in the chat. I've got the chat up as well, and I'll answer those as we go. Hopefully the audio's all good, and so yeah, just let me know if there's any issues with anything. Cool. All right. So what we're going to do is we're going to do a bit of theory intermixed with the 2020 past paper, which you guys don't have access to. So this will be good because it's something that you haven't seen before. Yeah. So we'll just kind of start at the top and work through. Yeah. Just stop me if there's any questions. And yeah, we'll just get stuck into it. The first thing I want to say about the midterm is it's going to be long. It's going to be hard, so make sure you prepare for it and work quickly through it. And there will be some Verilog. There hasn't been any Verilog in any midterms in past papers, so you might be a little bit unsure of what to expect. I had a chat to Bina, and it's pretty much just you're going to be asked to like interpret some Verilog code and maybe a test bench associated with that, and like talk about what it does. So it's not going to be super strenuous, but just make sure you understand and can read Verilog and interpret it and understand how test benches work in relation to that too. But I'll talk about Verilog a little bit at the end. But yeah, the point is you won't be asked to write a Verilog module in the midterm because that would be really mean. Sick. Okay. So let's get the first question. So we've got question one. So the paper's split up into two questions. Always a good idea to read through the entire thing so that you understand kind of what you have to do in the paper. But yeah, two questions, both 50 marks. 1A, we're given a function, and 1AI is saying find the total gate input cost of the implementation. So I want to talk a little bit about gate input cost, GIC, because it is a little bit confusing sometimes. So get rid of that. So your gate input cost is made up of three terms. It's made up of the number of literals, the number of terms, and the number of complements. So these might just be words at the moment, and that's okay. We'll talk about it with respect to the problem in a second. But literals are basically, if we were to look at the problem here, a literal is just a single letter. So each time you see a single letter, that's a literal. So we start by looking at this function here, and we think about how many literals there are in this one. We can count them from left to right, and there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the number of literals. So let's go ahead and write that one down. Cool. So there was 9 literals in that one. So literals are just the letters in the Boolean function. Cool. The other one we want to talk about was terms. So the terms is, you can think about it as like an input to a gate sort of thing. So in this particular one here, the input to a gate would be something like you've got CD. That entire thing, CD, would be an input to another gate. Therefore, we classify it as a term. So every time you see something ANDed or ORed together, that makes it a term. So if we were to go and I might just write this one out on the board actually, otherwise I'm getting confused. I'll just write this one down and I'll switch screen for you. So there's our function. And so what I mean by terms is basically everything that is kind of grouped together and not an individual kind of thing, because D would be like, you've already counted this as a literal, so you wouldn't count that one as a term. Okay, so I'm just going to kind of circle a couple of them. CD would be a term. CD plus D is also going to be a term. We've got A, C, D plus D. That's also going to be a term. So we've got 3 terms there. And then in the second half of the equation, we're going to do it again. 1 term here, 1 here, 1 here for the OR between the first 2 terms. And then finally, there's going to be 1 big term there. And then we're going to have 1 big OR over the whole of it. So each of those red lines represents a term there. So that would mean if we were to count those ones up, we'd have 1, 2, 3, 4, 5, 6, 7, 8, if I counted correctly. So that would make the number of terms that we have 8. Any questions about that?
Yeah, about figuring out how many terms there are. So it's a bit confused about what you did. Because let's say we have a term, because we say, like, for example, on the main term, let's say ABC is the main term. That'll be 1 term, right? Instead of AB and BC and ABC.
That's right. So you're looking for basically like the grouping of stuff. See how like you got CD or D? Yeah. You're looking at like everything that's ANDed together there. So CD is going to be 1 term there. So if you were to have something like F equals like A, B, C, as you suggested, because this is like one whole thing, that would be like 1 term because these are all ANDed together. So think about it as like when you would write that as like a logic gate, you're going to write it like this, right? It's going to be like that. And so what we're saying is that this thing here is just 1, right? Because we're ANDing them all together. So we could always kind of work out the gate input cost by drawing out the actual logic diagram. It just takes a while and probably don't have time in the exam. So if we were to count the gate input cost of this one, you'd have, what, 1, 2, 3, yeah. This probably wasn't a great example. I should have done something like plus D. But yeah, does that kind of make sense? Yeah. So you look for literals that are joined by the same operator without any brackets in between. Yeah. Cool. Awesome.
Individual ones, right? So that's how we have CD plus D and then you can count D.
So you count each individual one. So in terms of the number of literals, you go like 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. I get to compliments in a second because we do some tricky stuff with compliments. I just want to scroll through the chat. Yeah, Lucy's right. Not supposed to count that one. That's why I kind of added the plus D there to make that an actual term. What else have we got? Cool. Verilog will be at the end, Vincent. Okay. Yeah. Cool. Hopefully that's all the questions. If I missed one, just retype it in the chat. I wasn't looking for a second. Cool. All right. So the number of terms would be 8 for that one, and then the number of complements. We're going to look at like how many terms are complemented. We can see that like A is complemented here, and then D is complemented, and B and C, and also D again over here. Now we've got 5 complements there, but notice that we repeat the D complement twice. So we only count the D complement once. So if you think about it, if you like were to draw this up as a logic diagram, you would just have D, and then you would just pass it through an inverter once, and that would be your D bar, and that would be your D there. So you only invert it once in real life, so we'd only count the inversion once in your function. So the number of complements here, because we've complemented every single variable, that's just going to be equal to 4.
Yeah, one more question about when they said not counting the OR gate in the middle, I think they were talking about this example, saying that should be 7.
This one, yeah. 7. Yeah, actually, I think you're right. Yeah, my bad. Thank you for catching that, whoever caught that. Yeah, sorry. Because, and the reason why you wouldn't do that is because, yeah, gate input costs. So I guess if we look at the output here, like that's not going into anything. So the final output is not a gate input. It doesn't go as an input. Yeah.
It just goes to the same bar.
Yeah. That's it. Yeah. Yes, terms should be 7. Thank you. 7. Okay. Cool. So we got 9 literals, 7 terms, and 4 complements. If we add those up, we're going to get 20 in total. So the gate input cost for this one is going to be 20. So in example, yeah, cool. Yeah. 7. So the total gain cost is going to be 20 for that one. And then we're going to basically go through the rest of the question, which is going to go through optimizing it. And then we're going to do the gain cost again on the optimized function and work out the difference between the two. So back over to the paper. We've done the gate input cost, we came up with 20. And then we're going to now talk about f as a sum of min terms. This is going to be a little bit spicy because now we've got to draw up a truth table really to find it as a sum of min terms, unless you want to expand that function. So I'm going to draw up the truth table now and work out the sum of min terms for that one. So let's write out the function again. So we've got our truth table here, and let's just quickly write this out. Okay. So if we were to fill out this truth table, there's a couple of ways that we can do it. We can go through and insert every single value into the function, which is rather tedious, or we can kind of hack it and look at like when exactly this function here is actually true. So what I like to do is I like to treat it in kind of terms. So I'm going to look at the left-hand side of this one first and say that, okay, first I'm going to work out exactly when this particular term is true. And I'm going to fill out the truth table accordingly. So that particular term is true when A is false. We can see that by the A bar there. Like A has to be false for this to be true. So that means that we're only going to be looking at these values here. They're the only possible values there for which the left-hand side is true. And if the left-hand side here is true, this thing that I've underlined in green, if that is true, then that means the entire function is true because this is an OR here. So if either of them are true, the whole function will be true. Cool, so then let's look at the other condition on this first term, which is CD plus D bar. So this is going to be true whenever D is false because this one will be satisfied. So whenever D is false, we immediately know that we're going to have the output F being true. So I've just placed a couple of ones there for wherever D is false. We've also got C and D. So this term will also be true when C and D are both true. So I'm talking about this one here. So if C and D are both true, I'm just looking at these guys here. That's going to be here and also here. Now, because the second term is only going to be true when A is true itself, that means I can just fill the rest here with zeros. So that's pretty chill there. Cool. Let's look at the second term then, which is the right-hand side, and think about when that will be true. So that will be true when A is true. So we're immediately looking at the second half of the truth table because that's when A is going to be true. And then it's going to be true when both B and C are false, or C is true and D is false. So let's look at the first one, B and C both false. That's going to be this one and that one, because that's when B and C are both 0. The second half of that one, C is true and D is false. So C is true, D is false. That's going to be one there. C is true, D is false. Another one there. Cool. And then we just fill with zeros. So that's a relatively fast way to fill it out. And just looking at each term of your function. I can do that because they're ORed together. So if this term or this term is true, the entire function is true. If it was an AND, I couldn't do that. I would have to do some more stuff to it. Cool. I've filled out the truth table. Now it's asking me for the min terms. And so we're going to go and write this as a sum of min terms. And we're just going to list the numbers where it's true. So remember with the minterms, they're just whenever the function ends up being true. So we're going to go and list out 0, 2, 3, 4, 6, 7, 8, 9, 10. I've lost count. 8, 9, 10, 14. Cool. And that's the sum of minterms there. So yeah, probably easiest to fill out the truth table because we're going to have to do it anyway for part 3 of the question, draw a truth table. So we've already done that. And then just find it as a sum of minterms. Cool. Part 4 is, any questions about how I worked out the function f being true? All good? Sick. Cool. And then for part 4, where are we? Simplify it using a Kmap and express it as a sum of products. And we want to list all the prime implicants and essential prime implicants. Fun times. Okay, so I'm just going to go and move this elsewhere so that I don't lose it, but it's not there. And I'm just going to truth table.
When we're doing these,
question?
do you
No,
have
cool.
any problem with us having these truth tables in this case?
Oh, can you say it again?
For the actual midsem, do you have any concern with us using pre-filled out truth tables or Kmaps? So in this case, on that previous truth table you just made, we only have to fill in the F. Is that fine?
Yeah, that's totally cool. I think that's probably a good idea. And a couple of them have it. At least the structure that I copied, like on the left here, that was in one of them. But yeah, no, that's totally cool. You're probably going to be asked to fill out at least one of them, so not a bad idea. Kmaps themselves are pretty chill to draw, and it will depend on your variables. Like we have like A, B, C, D here, right? But what if it was like W, X, Y, Z? And that just will get confusing. So yeah, totally up to you. But I think pre-filling stuff's okay. Yeah.
Too easy. Thank you.
All right. Cool. So truth tables. Kmaps. So with this one, when you're doing your Kmaps, remember that it's grey code along the top and the sides. So there's going to be like 0, 0, 0, 1, 1, 1, 1, 0. Let's do this one as well. And that will affect like how you place the F values in there. So I'm just going to also go ahead and do something like this to say that that's when C is true. That is when D is true. A and B.
Is the team changed?
Sorry?
It's still on the team. It's still on the.
Thank you. Thanks for that.
Thank you.
Yeah, cheers. Sorry, so to, remember this is grey codes along here. Well, that's not very big. Cool. Remember that's grey code along here and along here, was what I was saying before. And yeah, and I usually put the letters at each section here to make it explicitly clear and helps us to kind of write the function as a sum of products as well. Cool. Awesome. So let's go and fill out the table. And so bearing in mind it is grey code, so when we fill this out, we're going to basically do a weird sort of pattern. So if we talk about the very first 4, which are these 4 here, that's going to look like 1, 0, 1, 1, and we place it like this: 1, 0, 1, 1. So we kind of skip and go to like this value and then that value. Cool. Let's keep going. So let's talk about the second one, which is going to be 1, 0, 1, 1 again. Cool. Let's talk about the third one, 1, 1, 1, 0. And then we're going to start down here because we're doing grey codes. So we're going to fill out the bottom row first and then jump into the middle. And the very last 4 are going to be 0, 0, 1, 0. And going to look like that. Cool. So there's our Kmap. And now let's go and work out what our prime implicants are and then talk about the essential prime implicants. So the prime implicants are basically boxes that are either like 2 by 2, 1 by 1, 2 by 1, 4 by 1, 4 by 2. They have to be like a multiple of 2 times a multiple of 2. So you can't have something like a something like this. That doesn't work. That's not an implicant, right? Because you need to have something that would be 4 by 1 in this case. So if we were to draw out all of the implicants in this one, or the prime implicants, so the difference between an implicant and a prime implicant is this would be an implicant, right? It's just a 1 by 1 square that works for us, but we can make this one bigger, specifically by drawing something like this. So that would be a prime implicant because we can't make that box any bigger. So when we're doing these Kmaps, we don't want to really look for implicants, we want to look for prime implicants because they're going to help us with our sum of products. Okay, so everyone clear on the difference between like an implicant and a prime implicant? Hopefully. If not, let us know. Cool. So let's go and find all of the prime implicants in this one. So the first one I kind of already circled was that one there. So that's just a 2 by 2. We can't make that any bigger. The next one would be something like this. So we've got the 1 by 4 square there. And what else do we want? We want this one here. I'm going to draw that in a different color because otherwise it's going to get confusing. Cool. So that's one as well. So these can wrap around the edges, remember? And then finally, I'll draw some in green. We have this one down here as well, because this one is kind of like the biggest we can make that to, so just a block of 2. Can anyone see any prime implicants that I've missed? Yeah, exactly. So this one's a real sneaky one, but like this. Yeah. So that's a real sneaky one, but because it's at all 4 corners, it comes together. Yeah, that's right. You guys got it. Christian asked would it be better to go with the corners. Yes, but then you've got to talk about this guy here, because you still got to include him somehow. And so, yeah, we'll talk about that in a second. So these would be all the prime implicants, and then when we're choosing the essential prime implicants, we'll talk about which of these we're going to choose. All right, so we've got our prime implicants. Let's just write them out. So I'm just going to say the prime implicants are going to be, okay, now reading off the truth table, when you do this, you're basically looking for variables that match. So if we were to talk about let's talk about this one first. So the 4 up in the top right, we can see that this one corresponds to C being true and also corresponds to A being false. So because this is like taking up a quarter of the Kmap, it's only going to involve 2 variables. So yeah, this is just going to be in terms of prime implicant, we're going to say it's going to be C true, A false, like that. Cool. Let's list the other ones out. So if we were to talk about this one next, that would be when C is true and D is not true. Something like that. And what about the one in blue? The one in blue is going to be when D is not true and A is not true. Like that. Okay, the corners are going to be when D is not true and B is not true. And then this one in green down the bottom left over here, that one is going to be when A is true, B is not true, and C is not true. So the final one is going to be A is true, B not true, and what did I say, C not true. Cool. So there are our prime implicants. What about the essential prime implicants? So when we talk about the essential prime implicants, what we want in the essential prime implicant is a prime implicant that can't be covered by any of the other prime implicants. So it's kind of unique in that sense. So if we look at our prime implicants on the Kmap here, and we talk about the corner one, which was the last one that we drew in rainbow there, we can see that every single corner piece is already in a prime implicant. And so we don't really need to include that in our final essential prime implicants because it's going to be covered by everything. The reason why is because of this guy here. this little one here requires that we have this green prime implicant. So that one's essential because that's the biggest one, the biggest square that we can draw, biggest rectangle we can draw that includes this one here. So basically your essential prime implicants are all the prime implicants that uniquely cover one of the ones in your Kmap. And then if you have like a couple that overlap at the end, then you can just choose which ones you want from there. But start with the ones that actually kind of need to be there to cover all of the ones. So that's going to be, we'll start with the green one then. So that was A, B bar, C bar. And we're going for time. Oh, we're using a bit quicker. Cool. And then it's basically going to be every single one of the other ones apart from the corners, because we need them to cover all the ones in that one. How is A, B bar, C bar a prime implicant? So A, B bar, C bar is going to be that green one, right? This is getting a little bit messy. I might just redraw this a little bit. So we're talking about this green one here, yeah? Mohammed? So that's a prime implicant because like we can't make that green rectangle any bigger, right? So if we try to extend the green rectangle to the left, which would wrap around over to here, we can't do that because that would make something like this, which doesn't make sense because there's a 0 in the middle. So we can't go extend that rectangle that way. If we were to extend it, for example, up, that also doesn't work because now we've got zeros in that square there. And if we were to try and extend it down, then what we'd end up with is that on top as well. And because of the 0 here, that also doesn't make sense. So can you see that we can't make that, that rectangle down the bottom left any bigger than it already is? Hopefully. Yeah, sick. Awesome. Good to hear. Cool. Back to the essential prime implicant. So it's going to be basically all the other ones apart from the corner prime implicant. So that's going to be what? C A bar, C D bar, and D bar, A bar. So that would be our essential prime implicants there. Cool. So the next part of the question, sorry, we're still going to make it as a product of sums. So as a product of sums, that's just going to look like basically the 4 terms that we wrote as our essential prime implicants as a Boolean function. So that's just going to be f equals A, B bar, C bar, plus C, A bar, plus C, D bar, plus D bar, A bar. Cool. And that is our sum of products form, or product of sums. Cool. No, I've got it the wrong way around. I've done sum of products, haven't I? Whoops. Rip. Okay, we can do product of sums as well. Probably a good exercise to do both of them. So product of sums is just the opposite in that we basically do squares around the zeros. So in this case, if we were to do it for this one, it would probably just be something like that, and like that. I won't go through with it because it's going to be like, yeah. Oh, 4. Oh, rip, sum of products. It was sum of products. Then it says to do product of sums. Yeah. My bad. Yeah, flick to the whiteboard. Yeah. Sorry, I'm reading the wrong part of the question. So I'll go to the whiteboard in a second. Part 4 was do it using sum of products, which we did. Cool. Part 5 was do it as a product of sums. I don't particularly want to do that because it's going to take a long time. But in terms of how you would do it, sorry for those that were watching online, basically you just do the same thing, but with all of the zeros in there. Yeah, same sort of vibe there. And it's just slightly different how you write them out because you write them as sums instead of products here. Okay, I'm going to skip that part in the interest of time because it's going to take forever. Okay, So now it asks us for our sum of products form, find the reduction in total gate input cost. So let's quickly do that again. So for our function that we found here, let's count our gate input cost. So remember, it's number of terms plus the number, of literals plus the number of complements. So if we count let's start with the literals first. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's nine literals there. If we look at the terms, we've got one term here, one term here, one term here, one term here. So that's going to be 4. And then the number of complements. So we've got B, C, A, D, D, and A again. And so remember that we only count them all once. We've got complements for A, B, C, and D. So that's going to be a total of 4 complements. And that makes a total of 17, or a saving of 3 gates, because the initial gate input cost for this function was 20. Cool. Yeah, use the zeros for product to sums. Yeah, thanks, Alex. Yeah, cool. Yeah, you could probably use De Morgan's and the complement sort of vibe to go from sum of products to product to sums. That's right. Cool. All right, draw the logic diagram. I'm sure you're all very capable of drawing logic diagrams, so I'm not going to do it here. So we'll move on to part B. Part B is base conversion, so moving between different bases. And so this one's quite easy because it's given us an octal and we want to go to hexadecimal binary. And luckily, it's very easy to move between these bases because they're all in multiples of 2. So if we go and write this out, I'm just going to make a new, we'll share the thing in a second. So octal was 654.7. Okay, so we want to go to binary as well as hexadecimal. I'm going to go to binary first because it's nice and easy. So if we go to binary, all we do is we just draw the decimal point, and 7 in binary is going to be 111. Pop that down. 4 in binary is going to be 100. It's worth noting that these are all 3-bit numbers. So octal is represented with like 3 binary bits. And so, for example, if there was like a 2 here, then that would be represented by 010, which would look like that. So you got to remember, you can't just write, 10 as in, because that's what 2 is in binary. Because we're working in octal and it's represented by 3 binary bits, we want to have that 0 there so that this is representative of the 2. Anyway, that's not actually that question. So let's get rid of that. Cool. 5 is going to be 101, so we're going to chuck 101 there. 6 is going to be 110. And there you go. There is your binary form of that number. Cool. So that's nice and easy. The next part of the question is talking about making it hexadecimal, which thankfully is very easy to go from. I'm just going to write hex because, yeah, screw that. So with hexadecimal, from binary to hexadecimal is really easy as well, because all we do is we group it in groups of 4. So let's start with a decimal point. So write the decimal point and a group of 4. Now, if you can't make a group of 4 because it's at either the start or the end, you just chuck zeros on the end. So 1110 is going to be in hexadecimal the character E, and 1100 in hexadecimal is going to be C. 1010 is going to be A, and then the last one is this 1, and we're just going to pen 3 zeros on there to make that 0001, which is just 1. So your hexadecimal is 1AC.E. So that was a really easy question because as soon as you went to binary, the hexadecimal was really evident. So just kind of be aware of these tricks for moving between them. What if I asked you for base 6 though? How would you go to base 6? Yeah?
Online calculator.
So yeah, not my calculator. That's actually pretty fair. I'd probably do that.
It's something with dividing by 6.
Yeah, that's right. You'd probably lose marks because then you're working in. Anyways, if we're going to do base 6, yeah, what I do is I start with the decimal version and then do divide by 6 and so on and so forth. So I'm just going to start with a completely new number to avoid having to convert to decimal in the first place, unless someone wants to quickly work out what that number is in decimal, but I can't really be bothered. So let's just start with an entirely new number. So if we're going from base 6, and let's say that our decimal was something like, I don't know, 123.61. That was our decimal. When we're going to base 6, I should write base there so it's clear. What we do is we do it in 2 parts. We do the integer part first and the fractional part. I'm going to do the integer first, so I'm just going to write the integer here. And all you do is you divide by your base number, which is going to be 6 in this case. So we're going to divide by 6. In calculator. So 123 divided by 6 is going to be 20.5. And so what we do then is we look at whether or not, oh, this is not going to be fun. So we have to look at the remainder. So it's going to be 20.5, which is the same as 20 remainder 3. And so what we do is we put the remainder over here, and then we drop the 0 point, we put the remainder there, and then we put the 20 down here. So we take the integer part and drop it down again. And then we repeat this process. So we divide by 6, which is going to be 3 remainder 2. We put the remainder over here, and we take the 3 and put the 3 down here. Divide by 6 again, and 3 divided by 6 is going to be 0 remainder 3, and so we carry the 3, and then once we get a 0 down here, we stop. Okay, so how do we read this out? Well, it's kind of logical, because if you were to divide by 6 again, you would get 0 remainder 0. So you put the remainder there and carry the 0 back, and you would just keep getting zeros down here. So that makes sense that this is the most significant digit, and this is the least significant digit. So in order to write that as like a base 6 integer, that would be, I'll write it in red, 3, 2, 3, because I'll be writing up here. So we start with this 3, 2, 3. Okay, so that's how we would convert to base 6 for the integer. For the fraction, it's very similar. We're just going to take the fractional part, 0.61, and now we're just going to multiply by 6 instead. So when we multiply by 6, calculator, cool, we get 3.66. And so what I'm just going to do is I'm going to move this over a little bit more. And so I'm going to leave the integer part over here and drop the fractional part down over there. And I'm going to repeat this process over and over again until I get to 0, effectively. Now, this is probably going to keep going on forever and ever and ever. And so the question will specify how many decimal places, usually like 2 or 3. So let's just do 2 decimal places, 2 base 6 places. Cool, 0.66 multiplied by 6 is 3.96. We carry the 3 and put 0.96 there, and we're just going to stop there because we just want two places. Now we read these ones the opposite of the way that we read the integers. So if we read the integers going up, we read these ones going down. And so basically this is going to, for the decimal place, just going to be 3, 3. So that would be our base 6 representation of the number 123.61. Okay, Leon says, that's a long question, let me expand it. If we're given octal, hex, or binaries, okay, use shortcut method of grouping bits, or do we always have to use long method? No, just group the bits. That's super chill, as long as you kind of show in your working that you're grouping bits, as in like kind of, you saw what I did, I was just throwing boxes around. If you do something like that, I think that's totally fine because you show that you know how to convert efficiently between those bases. Cool. All right, so that was B. How are we doing for time? Oh man. Okay. Part C was a flip-flop question, so don't worry about that because you haven't done it in lectures yet. you've done Verilog instead. Boolean algebra. So we might very quickly do this proof. Then we'll talk about using multiplexers to design a system, and then I'll quickly go through some Verilog. So we might go a little bit over time. Hopefully there's not a lecture after this. Cool. So let's have a look at question 2A. I'm just going to write this on a new whiteboard.
There's one more question.
Oh, thank you. Zach says, so where do we stop for the decimals and basics? It'll be specified in the question, so they'll just say stop at like 2 digits or 3 digits, or if they're mean, they'll say 4 digits. So just read the question. Yeah, does that make sense, Zach? Yeah, sweet. Cool. So let me just write this Boolean function down. Boolean identity. Okay, so I've written it there, and this is what we want to prove. We want to prove that x plus y is equal to x XORed with y plus xy. So remember that this little plus inside the circle, that's an XOR. And the truth table for that looks something like, so it's only when either A or B is true that the output is true. Cool. So this one's a little bit of a tricky one. General approach for Boolean algebra. You can do things to both sides, but it's generally easier to minimize the bigger side rather than to expand the smaller side. And so what we're going to do is we're just going to basically expand the right-hand side a bit, because what we should probably know is that if we were to, with that, or maybe I can, I know, I undid it. That's okay. If we were to expand this into the truth table that I had before, and we were to solve it using a sum of products form, what we actually get, we get x y bar plus y x bar. And this is much nicer to work with because we don't know how to deal with the XOR operator when we're doing Boolean stuff. Cool. So that's the first step, is to expand that XOR out. And then we're looking for ways that we can reduce it to just the 2 terms on the left-hand side. So the first one's pretty easy. All we're going to do is we're just going to take y outside of x bar plus x. So I've literally just taken these 2 terms and factored out the y. And we can see that when x is ORed with x bar, or x bar is ORed with x, this is always going to be true, because if one is false, then the other has to be true. So one of these terms is always going to be true. And therefore, we can just simply write this as, oops, I forgot the OR, as that. Cool, we're halfway there now. And then we're going to use one of your identities from the lectures, which pretty much just states that this is equal to x plus y. The formula for that is to look for something where you have a variable here, you have the complemented version of the variable, and you have a random other variable there. I'm not going to prove it, but you just got to assume that's true. It was in your Boolean proof slide in the lecture. But yeah, that's the general idea here, is that when you have the variable along with the complemented version ended with the x or another variable there, then you can just say this is equal to x plus y. So I think that was, if you're looking for the actual one, I think it was called simplification, which is really intuitive, but that was the actual technique used there. For this question, should we be writing the identities we use to simplify, or is it unnecessary? I think that if you do something like this, so you write down what identity you use next to it on each step, I think that will make it really clear for the marker. And I wouldn't expect you to do anything else. Yeah, otherwise you can spend all your time writing down the identities. Okay, hopefully that's pretty clear. So that was a reasonably simple one. And I don't have time now, but I'll give you guys access to both this midterm and my solutions probably later today. And there is part 2 of this, which is basically using what you just proved to go ahead and find an expression for this guy in terms of just XOR and AND gates. So yeah, apologies, don't have time to run through that now, but I'll give you guys access to that. Did I say it was good to do so? Yeah, I think it is a good idea to go and write these sorts of things down that show kind of what you're doing. Otherwise, this just seems like a kind of slightly illogical step. There's no factoring or anything there. I wouldn't write down that you're factoring stuff. That's pretty obvious, but for simplification, yeah, I would, or something like consensus, then I would definitely write down the steps involved. Okay, we're going to jump down to the part C, which is dealing with multiplexers. So multiplexers can be used to implement any Boolean function. You would have done this in the lab already, hopefully, if you've done lab 3. So we're just going to run through this one quickly. What have we got? Design a digital system with the following characteristics. We've got 4 inputs A, B, C, D, and 1 output Z. Z is true when A, B, C, D is less than or equal to 7, and the binary input value is odd. When it's greater than 7, oh man, okay. Let's go ahead and draw up the truth table for this one. So, maybe I'm just gonna copy that. Yes. Oh no. Oh well. Okay, so I'm just going to write this onto the whiteboard and I'll share the whiteboard with you. So we've got Z true when A, B, C, D is less than or equal to 7, and A, B, C, D is odd, and A, B, C, D greater than 7, and B XOR C. Okay, so that's our design there. Let's go through and work out what the truth table looks like. So for A, B, C, D less than or equal to 7, I'm just talking about these ones. And A, B, C, D being odd, so that's going to be whenever D is 1. So we're just going to go 1, 1, 1, 1, put some zeros there. And then for here, we're going to go and say ABCD greater than 7, so that's going to be the bottom half, and it follows B XOR with C. So remember that this is true when only one of B and C is true. So that's going to be looking at the B and C columns, that's going to be here and here, those 4 there. All the other places, B and C, are the same thing. Cool, so we filled out the truth table, and now it asks us to express it as a sum of min terms. We're going to skip that, and we're going to talk about how you implement it in part 3 with a 4x1 multiplexer. So with a 4x1 multiplexer, that one looks like this, right? And we've got 2 select lines and 4 inputs. So that's our mux there. So how are we going to do this? Well, they've kind of given us a hint and told us to use this 4x1 multiplexer. And by doing that, they're saying that we should really be looking at our output in groups of 4. So remember how a multiplexer works is that based on the select lines here, S0 and S1, one of these 4 is kind of routed through to the output. So if S0 and S1 are both 0, then this, let's label these as A0, A1, A2, A3. So if S0 and S1 are both 0, that's basically going to mean that A0 is routed to the output. If they're both, if they're 0, 1, then that's going to, I should have it the other way around. Let's just write the most significant bit at the beginning. Cool. If we would have them as 0, 1, then that would mean that the first one. So basically you interpret S0 and S1 as a binary number, and whichever one that is, you just connect the input corresponding to that one to the output. So what that means is we can use S0 and S1 to basically determine which of these inputs we connect to the output. So if I go ahead and say that, let's just get rid of these. If I go ahead and say that S0 and S1 should be A and B, what that means is when A and B are 0, A0 is connected to the output. And let's have a look at our truth table. That corresponds to these 4 entries here. So we want to look at these, and whenever A and B is 0, basically A0 should represent F, because that's going to be connected to our output over here. So now if we go and have a look at these 4 values of F here, we can see that they follow a particular pattern in that they're actually equal to D for those 4. And so what we can go ahead and do is we can go and say, right, well, I'm just going to connect D to this particular input to the multiplexer. And that means that whenever S1 and S0, which we've connected to A and B, are going to be 0, it will select A0, which will be D, and the output will be D. So we're just going to write a sneaky D there. And so that's how that one is the first 4 work. With the second 4, it's actually exactly the same. Again, it's D. So we can see that the output follows D for those ones. And so we can just go and place D there. And then for A2, what have we got? For the next 4, which is these ones here, the output becomes a little bit more interesting because it now no longer follows D. So someone will tell me what I should be doing for that one.
You should pop C through it.
C, yeah, because we can see that we've got 0, 0, 1, 1, and it follows C there. So that's really easy as well. So we can just try C there. All right, the last one's actually kind of interesting in that we can't actually do that anymore because 1, 1, 0, 0 doesn't follow any of the variables. So does anyone have any idea? Yeah. Complement, yeah, complement C. So we can do this again. That was actually a really easy example. Slightly harder one would involve something like, for example, let's see if I can make that a little bit more interesting. If we were to change this one to a 0 here instead, now it no longer follows any of the patterns. But all we do then is we just try and arrange this in terms of, again, C and D. We can't just hook one of them up because that doesn't work. But what we can do for this 1, 0, 0, 0 output is say, no, hang on, that looks familiar. That looks like a NAND gate. So what we can just do is we could just have a NAND gate with C and D connected to it. And we know that's only going to be true when both C and D are false. Did I get it right? And not quite, because the end is like, yeah, it's a NOR, is it? Yeah, that's right. Sorry, NOR. Thank you. But yeah, you're just basically looking to, let's write that again. Right, that was a lovely NOR. C, D. You're looking to try and construct this as like a mini truth table in terms of just looking at these ones. That wasn't a very good color. Just looking at these values here and seeing if you can work out what the function f is in terms of those. So if you're asked to do this with a slightly different size decoder, yeah, Miriam's got it. Thank you in the chat, I just looked. If you were asked to do this with a different size decoder, for example, an 8-to-1, multiplexer, you just do the same thing, but you just go ahead and group it in groups of 2 instead. And similarly, if you had a 2-to-1 multiplexer, you would group it in halves. So yeah, that's kind of how you deal with those sorts of questions with multiplexers. Any questions about those? All right, real quick, because I think there's a class coming in.
There is, but we might be able to do it next door.
Yeah.
If you want to take a bit longer to answer some questions.
Yeah, I will do that. I just want to quickly run through Verilog for like 30 seconds. So remember what I said at the beginning, you're not going to be asked to write Verilog, you're going to be asked to interpret Verilog. So yeah, you can see that good. So just to give you a quick recap, there's 3 different ways you can write Verilog to achieve a purpose. You've got data flow modeling, behavioral modeling, and structural modeling. What do they look like? Data flow modeling looks like this. And so I pretty much just copied the slides here, but you can see that you've got this E and F being assigned to this function here. So it looks very much like a Boolean function. So really chill. You can just treat that as a Boolean function. It shouldn't be a problem at all. So that's data flow modeling. Structural modeling is basically how it looks like on the logic diagram if you were to draw the gates out individually. So that's just like AND, G1, W1, AB. That can be a little bit confusing, but your output comes first for these gates. So W1 would be the output, and then A and B would be the inputs to that particular gate. And so the best way to think about these ones, I think, is to basically just draw up the logic diagram it corresponds to, connect it all up, and then try and answer the question. The third way you write Verilog is behavioral modeling. And so behavioral modeling looks like this. Typically got an always out. This is for a multiplexer, a 2-to-1 multiplexer. And there's a couple of different constructs you need to be aware of, one of them being an if case. So this one's like, if the select is 1, then you do this, otherwise do that. So hopefully you're familiar with C and you can roughly follow what's going on there. Question?
Oh yeah, the structural modeling one,
Yep.
which gate comes first, is it like the not gate?
So they can be ordered in the Verilog in whichever way whoever wants to display it as.
Yeah, so
but
like the time they're given there in that example, which gate is like the not gate comes first,
so that one would be the not gate here.
and then like the or and then and.
Yeah, so you just look at that. The input's E and the output is C, right? And so, sorry, output is E, input is C. Outputs come first. So you can kind of see that on the diagram there. And basically what I do is I just draw the not gate. I'd label the output and the input, and then I go and draw another gate and then connect them up like so.
Because it's like differentiate with like the time scale, like it's not the hashes.
With a time scale.
Like the hash 10.
No, so with structural modeling, so with the hash stuff, that's only in your test benches. So the hash is just a delay for your test benches to basically let you differentiate between different input sets. So yeah, the hash 100 whatever doesn't make sense as actual Verilog. It's not code, it won't compile. Actually, it might compile, but just won't work. So if you see a hash 100, it's going to be a test bench, and it's just saying, give a particular input, wait 100 nanoseconds, give another input, so that you can see a nice waveform on your graph. Does that make sense?
Yeah.
Cool.
Okay.
Yeah, people in Teams, if you want to hang around and I'll answer questions, I'm just going to jump over to another room because we've got a lecture coming in here. But yes, I'll make this all available to you. I'll probably add everything into the post I put in Teams. So keep an eye on that one. Thank you very much. Catch you later. Yeah, cool. Cool. So the first one's priority encoders. So what's the best way to explain this? Probably by drawing something. Let's go and just make a new whiteboard. Hopefully appear on the screen there in a second. Okay. So a priority encoder is like an encoder, but its truth table is slightly different. Perhaps an Excel would probably be better for this one because I was working on my computer. So if we have a 4-to-1 priority encoder, so it's going to have inputs of like A, B, C, D, and then it's going to have 3 outputs. The outputs are going to be V for valid, and then let's just say O2 and O1. So that would be the 2 outputs here. So for our inputs, we could go out. Oops. So the priority encoder works by basically this is your inputs, and it prioritizes the output based on what the inputs are. So A has the most significant influence on the priority encoder, followed by B, C, and D. So really, actually, I didn't actually need to type all them out. Let's just get rid of them. Because of that, what I'm trying to say is that if A is 1, it doesn't matter what B, C, and D are. The output is going to be 1, 1 in terms of O2 and O1. So it doesn't actually matter what B, C, and D are. If A is 1, that just means that the output is going to be 1, 1. So that means that we can kind of simplify this truth table a little bit. And oh my God, how can I delete multiple cells? Cool. And we can do something like this. So put a whole heap of don't cares in there because if that was supposed to be 1. If C is 1, if B is 1, for example, it doesn't matter what C and D are because B has more influence. And so I'll draw up the entire truth table in a second. Cool. And so what that means is I'll get to valid in a second. Just ignore the V output there. But for O2 and O1, it's just going to be like binary counting. Like this. So if A is 1, it doesn't matter what the rest of them are. The output's going to be 1, 1. If B is 1 and A is 0, then the output is 1, 0, irrespective. And so you can see that like the only time that we get 0, 0 is when D is 1 and everything else is 0 there. Cool. So then let's talk about the valid output. The valid output has to distinguish basically between the case where everything is 0 and the case where we have something being 1. And so this valid is basically 0 for the first one, and then 1 for everything else there. And so the valid, it doesn't really matter what the outputs are here because the valid just means like basically ignore this. So we could have them as X's or zeros. But yeah, that's the idea behind a priority encoder. There's the truth table for you there. So they're your inputs, and these ones are your outputs. I'll put them in, whoops, red. Cool. Was there any questions about the priority encoder then? Let me just scroll through. Yeah, pretty much. So it's just basically the most significant bit of A, B, and C, D. Yeah. Cool. That was priority encoders. Is there any questions about priority encoders? No, they're pretty chill. Trying to think if there was an example of one. Use of a priority encoder. I think 2018 might have had one. I don't know that I have it here. Where did I put it? Yeah, 2018 I think has a priority encoder question, but you have solutions for that as well. Cool. What was the next one? How would you draw one? Yeah, like a normal encoder, I think, except you just label it with a priority encoder. I do have the solutions for this somewhere for that particular exam. It's just an encoder. Oh yeah, yeah. You just kind of draw it like a regular encoder. So over here, you would just basically, your encoder is a block, and so you've got your 4 inputs to it, and then you have your 2 outputs, and then also the valid line. So where do I write text? Here. So that would be V. And then this one would be like your O2. Oops. Okay, yeah. So it's going to take forever here, but like probably Paint would have been better. Paint's a great program. Why can't I see that? It's so weird. Okay, anyway, O2 and O1. I'm going to use Paint. So much better. All right. Look, you can draw boxes. Oh no, that's not very nice. There we go. Okay. Anyway, V and then S2 and O2, O1. So oops. V, and so you probably just say that this is a, priority encoder. You just write that on there to make it explicit. And then, I don't know, I0 through to I4, or you could do AB, I3, or you could do ABCD, as I've done in the Excel spreadsheet there. But yeah, that's the priority encoder. But yes, the point of having a priority encoder is so that using this valid line, you can differentiate between the case where you have all inputs 0 and the case where you have 0, 0, 0, 1. And yeah, you can also basically, just have the most significant bit carried through to the output. Cool. Last year's paper, probably not uploaded. So I went through the 2020 paper for this one. So I'll upload that one for you guys somewhere. I'll probably just send a Google Drive link in your general chat on the Teams for 2141. And yeah, cool. Hope that answers the priority encoder question. There was a question about always statements in Verilog. Where is it? Over here. That one. Okay. So always statements in Verilog just mean that this code inside the always will run whenever A or B or select change. So there's a couple of different conditions that can sit inside the always block. Either when, if it's listed like this means like level change. So this always at block will run when one of these variables, A, B, or select change levels, either from 0 to 1 or 1 to 0. And the other way you can also write it is, it's not listed there, is something like, let's put a text box, where are we? You could also write it like always at something like pos edge of the clock. Now, you haven't done the sequential logic, so I wouldn't worry about that, and I highly doubt that something like this would happen in your exam, but in the random case that it does, that just means that clock would be a variable in your program. Let's make it more explicit by saying that this is like A, because A exists in your program already, in your module. If we were to say pos edge of A, that means that that always block will be run every time we have the positive edge of A. So not just on every level change, just on the positive edge of A. And so you can also do neg edge A. And if you want both pos edge and neg edge, that would just be level. So you would just, write it like you've got here. So usually your always that will be enclosed in a begin and end. This one isn't, because if your code consists of one line in inverted commas, you don't have to put a begin and end. And because this if else is chained together, it acts as one line, and therefore you don't need the begin and end. But usually you'll have like a begin and end around stuff. It's not here either, because the case acts as one line, so to speak. Yeah, hopefully that makes sense with how the always works, where teams go. So you would model flip-flops with like the pos edge clock sort of stuff. Yeah, so I wouldn't worry too much about that. I just thought I'd mention it just in case, but I don't think you'll see it. Cool. Any questions about Verilog before I move on to the last thing I wanted to talk about, which was, I think, making a decoder. I mean, if you look at the examples and lecture slides, you should be pretty chill for the exam for Verilog. Okay, no questions. All right, let's have a look at making a decoder from NAND gates, because I think that was the last thing that someone asked about. Yep, decoder. Designing a decoder from NAND gates. There is a design procedure given in your lecture slides, and so that's probably the best thing, is to literally just read off it. But to go through an example with you, if we were to use, our wonderful program here. Let's just say that we want to do like a 5-bit decoder. So that's like 5 input bits. 2 to the power of 5 is 32. So 5 to 32. Let's write that properly. 5 to 32-bit decoder. Yeah, you just pretty much follow the design pattern. And so the way to do that is basically to start at the end and to say that, okay, for a 32-bit output, I'm going to have 32 NAND gates, so AND gates at the end. And so we would just write a block here and just say this is 32 AND gates. And I'm just going to go and draw like an output coming off here. And that's just going to be, so we're going to represent that as a bus by saying something like that and saying 32. So there's 32 outputs there, 32 AND gates. And I'm just going to make this a little bit thicker. Yeah, much better. Cool. So we've got those 32 AND gates, and then we've got to break it down. So basically, we're going to like recursively apply a particular step, which I'll talk about in a second, until we get our 1 to 2, 2 to 1, 1 to 2, 1 to 2 decoders right at the very beginning. So what we do is we go and take our 2 to the power of 5, which is, I'm just going to also write that in here. So that's 2 to the power of 5. And we're going to basically break that into 2 blocks. And the size of the blocks, I'm just going to kind of chuck them down here. These are also going to be blocks of AND gates. And this one's going to be, you're just going to split this power in half. So 2 to the power of 5 doesn't split in half very well because it's an odd number. So we're going to split it into basically 1 up and 1 down from half. So that's 2.5. So we're going to do 2 to the power of 3 and 2 to the power of 2. So we're going to do 2 to the power of 3 and gates here. And then we're going to also do, I should probably turn that down a little bit. That's a bit overkill. 28. 2 to the power of 2 and gates here. Make that a bit bigger. Oh no. Yeah. So that's what we're going to do there, and then we're just going to basically draw lines into here. So this is going to have 2 to the power of 3, which is 8 wires going there, and this is going to have 2 to the power of 2, which is 4. Cool. And so I don't think you need to explicitly say what's inside these blocks because it should be fairly obvious what's happening there, and it's going to take you forever to write it if that's the case, as long as you demonstrate that you know this procedure. So then we recursively apply it, right? We look at the 2 to the 3 and we say, okay, we've got to break that into 2 blocks. That's going to be a 2 to the 2 as well as a 2 to a 1. Now when we get to the 2 to the 1, we say, okay, we can actually draw that because it's really just an inverter. So let's just draw out the 2 to the 2 first, and then we'll go and draw out the 1 to 2 decoder. Cool. So that's our 2 to the 2. We can go ahead and do this. 2, 4, and then we can go and draw our 1 to the power of 2. So 2 to the power of 1 lot of, well, AND gates. It's just going to look like this. When you get the 1 to 2 decoder, it's just going to be like an inverter. And the input is basically just going to be, yeah. And so it's just going to look like that. And so, yeah, that's your 1 to 2 decoder. And so we're just going to do that. For the 2 to the power of 2, we're going to break that in half again, have 2 lots of 1 to 2 decoders, which is just, again, going to look like this. So really, it's just recursion where your base case is the 1 to 2 decoder. Cool. And then maybe I'll just copy and paste this pop it down there. And so that's all there is to that. We would also have to grab these and pop them. Let's make a smaller version on here as well. And then you have your 5 inputs, 1, 2, 3, 4, 5, and your 32 outputs. So as long as you just recursively apply, basically breaking it in half. And the only tricky thing is when you have an odd power and you just break it into basically 1 up and 1 down from half. Okay. Would you go through how, okay, is there any questions about the decoder stuff, construction of decoder from AND gates before I answer the next question? Yeah, that's good. Yeah, sick. No questions, sick. Could I go through how one would find the gate input cost for this decoder? Okay. So how do I know what segments I need? What do you mean by segments? As in like the blocks that I drew? Yeah. So basically I broke it in half, right? 2 to the power of 5. If it was 2 to the power of 6, this would have been 2 to the power of 3 and 2 to the power of 3. Like I just kind of break the power in half and go like that. If it's odd, then you kind of 2 to the power of 5, or 5 divided by 2 is 2.5. So 2 to the power of 2.5 is just mean. You can't do that discretely. So you kind of do 1 to the power of 3 and 1 to the power of 2, such that 2 plus 3 equals 5. Does that kind of make sense, Zach? I can't kind of watch the chat as well as show you that. But anyways, maybe I can. Kinda. Okay. Yeah, I might answer some other questions, but if you have a more in-depth question, just feel free to type it out and I'll come back to it in a second. Could you go through how one would find the gate input cost for this decoder? Yeah, so I guess we just add up how many AND gates there are and work out how many inputs. So remember your gate input costs. I mean, like, if you just have like an AND gate, a regular AND gate, what's the gate input cost of an AND gate? Does anyone want to tell me? 2, 3, 6, 100. 2. There's 2 inputs to the AND gate, right? So the gate input cost of a single AND gate is going to be 2. So we can think about it. Yeah, you guys got it. We can think about this logically and say, okay, if I've got 32 AND gates here, as well as 8 AND gates here, 4 AND gates here, and 4 AND gates here, I'm going to have that many AND gates multiplied by 2, and that gives me the gate input cost for these blocks. Now, I've also got to calculate the inverters, which have a gate input cost of 1 each, so that would be add 5 to that. So what, 32 plus 8 plus 4 plus 4, so 32 plus 16 would be 48. 48 plus 5 would be 53. So that would be a gate input cost of 53, I believe. Cool. Does that make sense, Vincent? Oh, true. Yeah, thank you. I messed that up a little bit. 48 multiplied by 2. I forgot the multiply by 2. So what was that? 96 plus 5, 104. Yeah, good catch. 104.
101.
1, thank you. God, my maths is great today. Yeah, 101. Thank you. Cool. Any other questions from anyone or anything else you want me to go through? Cool. So basically all the, wait, hang on, and the single uncomplemented inputs for the 1 to 2 decoders. Yeah. Okay, so basically all the AND gates plus inputs. Yeah, pretty much for a decoder. Yeah, that's correct. All the AND gates multiplied by 2 plus the inputs. Yeah. Could I briefly go over tri-state buffers? Yeah, sure. Tri-state, I should probably make a new paint at this point. Tri-state buffers. They look, do I have triangles? Not really. All right. Tri-state buffers. They have 3 inputs, right? You've got, 2 inputs. You've got your regular input and then you have your enable. So here's your enable, and then we've got, let's just call it I or in, and then you've got out over here. And so the truth table for that basically looks, oh, this is going to be fun. I can't draw it out here. Let's drag this over here and pop that over there. So the truth table for a tri-state buffer is going to be like, you've got two inputs, your in and your enable, and then you've got your out here. So let's make them bold. So let's draw out the truth table. 1, 1, 0, 1, 1. Okay, so when the enable is 0, that just means that the buffer is turned off. And what that means is we can't represent out in terms of high and low anymore. Instead, we say it's high impedance. So when the enable is off, it means that it's physically removing itself from the circuit. And so the value over here we say is high impedance, or we say it's just going to be Z. So that would be our way of representing it in a truth table. And what that means is it basically kind of disconnects from the circuit by presenting something in the order of mega ohms resistance at the output. So that's kind of similar to basically removing this buffer from the entire circuit. When the enable is 1, it acts like a regular buffer, so the output follows the input, so 0 and then 1 there. Does that kind of make sense? So yeah, 3 states, high impedance, high and low, and the high impedance is just used to basically remove that buffer from the circuit from an output perspective. Yeah, sick. Anything else?
Sorry, but how's it exactly different? Like there's a high impedance and low impedance. Like how's it different from a AND gate?
Or like a regular buffer.
Yeah.
So like high would be 5 volts, low would be 0 volts. But imagine you had a chip and you didn't have anything connected to one of the inputs. What voltage would that input be?
Didn't have anything connected. All right.
If you can't tell, right? So that's what this kind of does. It basically says when the enable's off, it presents a high impedance, and that's what that would look like to someone who's over here. Say you had an AND gate here, taking an input from your thing. It would just look like you literally pulled that wire out of the circuit. Yeah. So it's different in that the voltage is not defined anymore, but it's like nothing is connected. It will probably inherently pull low, but like, yeah. Does that kind of make sense? Yeah. Right. Cool. How can 2 or more tri-state buffers be connected together at their outputs? Okay. So if we were to do this, it's probably not great practice, but you can do it. The moral of the story is that you shouldn't be ever connecting more than one thing to more than one output together, because what happens is if you have something driving that line high and the other one driving it low, like what voltage is it supposed to be? It's not like it doesn't work, right? So we try and avoid that. But what you could do is you could do something like this. Oops, where was it? Where we could just basically grab this and place another one of it down here, and we could go ahead and complement enable, and then do something like this. So and then what I'll do is I'll just call this in 1 and in 2. So basically, based on this one, if enable is true, that means that the first one gets passed through the output. If the enable is false, that means this one removes itself, and then in 2 gets passed through because this one turns on. So based on this enable and the complement enable, it's only one of these buffers is going to be active at any one time, and the other one will be disabled and removed from the circuit. And that's pretty much the only way that you can connect 2 outputs together. What is this actually? These 2 buffers, the tri-state buffers like this.
This is a 2-to-1 multiplexer. If this is our select line, if the enable is a select line, then we select either in 1 or in 2 based on the select. So this is a basic 2-to-1 multiplexer. But yes, not very good practice, I don't think. Although, yeah, I haven't really done a whole lot with connecting tri-state buffers together. So possibly best to do a bit of Googling about that. Hopefully that answers your question, Miriam. Anything else? Yeah, that would probably be the idea there. Okay, what paper was it from, out of interest? Yeah, the idea is that like you can do it with the tri-state buffers as long as you make sure that that like only one of them is enabled. So for like, okay, for more than 2, you would just make sure that only one of them is enabled at a time. Yeah, you'd have to design some more logic around the enables there. You couldn't just complement it because you'd have like 3 or 4 enables. So yeah, as long as you've only got one buffer, tri-state buffer active at any one time, then that should be cool. All right, anything else? Cool. All right, thanks for your attention. Do you want to stop the recording? Thanks, Jack. I don't know that I can. Awesome. Good luck for your exams. Have fun. Hopefully it's not too rough. Yeah, if you have any questions,